Okay, let's talk about protection and privileges. So to show you this concept, let me start by the following program. So I have this program called CR3-S. What this program does is it loads a value into register REX and move the register REX into register CR3. You probably have not seen the name register CR3 before in the introduction to assembly, but trust me, it's a real register. And the reason I know it's a real register is because if I try to assemble it, then the assembler does not complain. If I change this register, of course, to any other register, let's say CD3, if I try to do assembling, the assembler complains that there is no register called CD3. So therefore, I know that this is actually a legitimate register. So I can assemble this, and I can also link this CR3-O, or .O, they call the output CR3. And now the question is, what happens if I run it? If I run it, I get a segmentation fault. In other words, the program doesn't run and it is killed by the operating system. And the interesting point here is that there is no way to run this program. So what do you think happens if I try to execute this program through sudo? So sudo, as if you don't know, is essentially trying to run this program as the administrator. So essentially what I'm trying to tell my machine is that I, as the administrator of this machine, I really would like to run this program. Please run this program. So it seems like I should be able to do this because, I'm trying to run this with the highest level of authority that exists in this machine. As of course, it will ask for my password if I can enter it correctly. Let's try that. Okay, so I entered my password correctly. This program is being run by as the administrator. I still get segmentation fault. So now the question is, how can we understand this? Okay, let me go back to the slides again. So in the slides, I'm basically trying to do the same thing. We need to understand why this crashes. This is because this register is essentially part of a system register. There are lots of registers that you don't hear about them in any normal assembly code. This is because those registers and those systems are not for normal users. They are designed for users that have highest level of privilege. In particular, they're designed for operating systems. So this register, we're going to see it later on, can only be accessed by the operating system. If a normal user tries to do it, the hardware catches this and essentially notifies the operating system we will kill the program. So that's what was happening to us. The concept of privilege and having different levels of access can be implemented in many different systems. In particular, it is implemented in ARM architectures as well as in Intel architecture as well as some other architectures. Essentially, any modern capable hardware, a hardware that can run any of the modern operating systems should have such a support. The numbering and the notations and the terminology will be different. In particular, Intel numbers them from 0 to 4 or 0 to 3 as lowest numbers being higher level of privilege. ARM does it the other way around. But the concept is the same. So in Intel, level 0 is known as the kernel or the highest level of privilege. Essentially, you can do basically everything here. Level 3 is a user level. You cannot do much. You're only limited to the basic systems of the machine, and for everything else, you need to rely on the operating system. And pictorially, it looks like this. So this is pictures from Intel manuals. There is also this privilege level. Not only decides which instructions you can use and which register you can use, it also could decide which memory locations you can access. There will be, as we'll see, some memory locations that could be marked as super user. These are users that are in level 0 to 2, and as a normal level 3 user, you cannot access any of them. So if you look at ARM manuals, for example, that link up there, you'll see a description like this. So that ARM v6 exception model defines 4 exception levels, 0 to 3. 0 has the lowest, so this is like for normal users, so this is the opposite of Intel, and level 3 is technically the highest. And interestingly, in ARM, according to ARM architecture, the only mandatory implementation that exists, if you want to manufacture these chips, you have to implement level 0 and level 1. Level 0 is for the normal user, and level 1 would be for your operating system or the privilege instruction. All the other ones are not technically mandatory to be implemented. This is a short description of these, what they are intended to be used for. and a pictorial description over here. We're not going to look at hypervisors, secure monitors, all the stuff that's beyond the scope of what we are trying to do here. So basically what we want essentially is the two-level one, where you have the normal applications and then you have the higher privilege operating system. Okay, so that's where as far as we will get to. Okay. A question that you might be having is that how is it that the operating system ends up being in charge of the machine, and how is it that enters this super privileged state of operation? And the answer lies in essentially the way a computer turned on and is started. So whenever you turn on the machine or your computer, lots of complicated things happen. And as far as I know, not everything is public. So for example, if you focus solely on Intel chips, there is a lot of internal initialization that is going on, and I'm pretty sure a lot of it is trade secret. Intel probably doesn't want you to know everything about them. This is because if you look at the CPU as a very complicated circuit, the circuit has many different pieces. These pieces need to be initialized. The signals, there is power into the system, and the output of the circuits need to stabilize before we move on. So there are lots of initializations and stabilization that is going on inside the CPU once we add power to the CPU. Okay. At some point, CPU will be a working circuit and it will be operational. In an Intel machine, the way this works is that CPU starts by working only in a primitive and a basic mode. You can look at the manuals for the details of it. Here, I'm just going to go through it quickly to simplify things. Essentially what this means that inside this primitive mode, there isn't really the notion of security or privilege mode, all that stuff. But luckily in this mode, the CPU does not need to execute random code from the internet. It can only execute codes that is very trusted. So for example, from a read-only memory. Eventually, this chain of executions of the trusted code results in a piece of code that gets executed that looks for a bootloader. So in other words, looks for how to initialize and start up an operating system. Again, there is a complicated mechanism behind how these bootloaders are set up. For example, in Intel, you could have the first bootloader and the second bootloader, all that stuff. But ultimately, all of these operations are done under this privileged state of operation. Once this special bootloader is started, the operating system is loaded. And since the machine is inside this higher level of operation, it is possible for this piece of code to change the mode of operation and to access the system level services and circuitry. Intel again has funny names for different modes of operations. That is chips long mode is basically what you're looking for if you have a 64-bit Windows or Linux or whatever. So once we get to this stage, the operating system is running, and it is running at the highest level of privilege. And now you trust your operating system to set things up properly. So in this mode, the operating system can access control register, can set up interrupts, can set up virtual memory, as we'll see later, and as well as all the other parts of this machine. And once everything is set up, only then the operating system can run user programs. And once the user programs are run, they will be running in the normal mode or the user mode of operation. Okay. And to emphasize, OS is the only part or only program that can access input-output devices such as network, hard disk, and etc. So all the other programs need to go through OS through the system call mechanisms that we covered before. Okay. To summarize this, modern hardware includes many different registers and system level operations that are not accessible to the normal programmer, and only the operating system can access them. The operating system uses them to configure the system and make sure that the system is run correctly and with the security guarantees and all that stuff. And there are also well-established rules that designate how the operating system comes in charge, and also how this raising and lowering of this privilege level is done. And we're going to look at that later through the concept of system calls. Okay, just to give an idea of what are we talking about when we're saying the system level registers and data structure. This is from, again, Intel manual. So this describes different system level register that exists as like a summary plot, and again, this is the mode of operations that I mentioned earlier. Again, all of these details can be found in Intune manuals. They're thousands of pages long, but of course you do not typically want to read them unless you want to develop an operating system for it. So that summarizes the protection out of privileges, and later we're going to look at, I think, virtual memory.